Yeah, this is our EE128 project. It's called Magnetic Levitation, and we are Philip Tai, Chemini, and Farhan Turhi. Yeah. So our goal is to make a controller of this system so that the magnetic ball can float in the air. Okay. So this is the basic circuit schematic. So you can see there consists 4 stages: the sensing stage, the voltage buffer, and the controller, and then the output voltage to current converter. Okay. So at first we have a photoresistor as a sensor, and the photoresistor can only take a maximum power of 250 milliwatt. So we have to choose R1 so that the power flow through the photoresistor is less than 250 milliwatt. And by calculation, we found out because we use 7-volt rail to rail, positive 7 to ground, and we don't need. We can achieve less than 250 milliwatt of power by using any positive resistor. So we pick 500, and by using a resistor in series with the photoresistor, we can sense if there's a light different, the light emitted to the photoresistor difference, then we'll sense voltage difference across the photoresistor, and that's our sensor. And we choose 500 ohm, and you'll give us a Vmax of 5 volt and a minimum of 3 volt. And the second stage, because we want to fit the controller 0 voltage input so that when it's at equilibrium, the force on the ball stays constant. So when you feed 0 voltage to a controller, there's nothing happen there's no changing to the system, so the ball can flow into the air. And by doing that, we use inverting amplifier and a variable resistor at the positive input so that we can tweak the resistance and change the voltage at the output. So we set the output at 0 voltage. And notice that because it's an inverted amplifier, we have a 180-degree shift. So when the voltage at the input increases, the voltage at the output decreases. And let's go on to the next stage, which is the controller, which is the main design of this project. And the controller is basically a leak compensator. And we have, as you can see, R2 resistor and a capacitor. And that, if you do the transfer function, you'll give us a pole and a 0, and the 0 is before the pole. So we do some calculation and some measurement to find out that we need a gain of at least 5 to make sure the controller have a pole on the left-hand side. And so we choose gain of 5, which means we have a 2K R1, and we choose R2 to be 200 ohm because we want the pole to be 10 times further away from 0, so that we can have better pole. So the pole can move toward the left-hand plane quickly. And we choose C to be 10 microfarad because it gives us a phase margin of 60 degree. Yeah. And so that's our criteria in designing this controller. And notice again, we have an inverting amplifier there. And to do that, because we want to make sure the impedance looking out to the controller is infinity, so that it's large, so that the loading on the controller doesn't affect the behavior of the controller. And again, there's a 180-degree phase shift. So now we have a positive, because the previous stage there's 180-degree shift, and now there's another 180-degree shift. We now shift back to positive 0 degree. And next stage is current offset buffer, and we do that so that when at 0, when the ball is at equilibrium, we have enough force to lift the ball. So again, we use an inverting amplifier, and now we at the negative end we put a variable resistor so that when we can tweak the resistance looking down to the V minus. So when we change the resistance, we can change the voltage at the output node again, and the voltage will go to the current voltage to current amplifier 1-to-1 ratio, and by experiment we measured we need 2.4 volt to make ball to have enough force to lift the ball at equilibrium, and not too much force so that the ball doesn't get sucked into the inductor. And the next stage, this is the overall block diagram of this whole system. So at first we have a desired position, and if it's at equilibrium, it's 0, and the voltage feeding in to if they're equal, then you'll give us a 0 error, so the controller won't behave anything. And if there's slightly change, the controller will try to either increase or decrease the force. And the next stage is the current offset. So it's as I mentioned before, it's just so that when at equilibrium we have enough force to lift the ball in the air, and the current amplifier to convert the voltage to current, because the inductor takes current. And next, and this is a map that we model the system as a linear model, and this is second order system, and we use a state space technique to do the MATLAB. As you can see, by using a gain of 5 and then 0 at 50 hertz and pole at 500 hertz, we were able to move the pole initially at right hand side to the left hand plane, and we have a phase margin of 55 degree. That's close enough to 60 degree. And you can see, if we zoom in closer, the 0 is at the right hand plane now with a gain of about 5. And as a result, we're able to levitate the ball, not just 1, not just 2, but 3, and with some really amazing stuff. And if we tweak the if we tweak the last stage, which is the initial current, if we increase the current first, we're able to lift a much heavier ball. And as you can see from the picture, we have a big ball on top of a medium ball, on top of a small ball, and that's about 100 grain weight. Yeah, and